Have you ever felt that satisfying invisible pull just before a magnet snaps into place? A simple force, holding a note to your refrigerator door. It's a quiet, everyday marvel of physics, but what if we could harness that same fundamental force, amplify it beyond imagination, and use it not just to hold a piece of paper, but to peer deep inside the most complex structure known, the human body? Now, scale up that familiar fridge magnet, not by 10 or 100, but by tens of thousands of times. Imagine a magnetic field so powerful it could lift a car. What you're picturing is the immense silent heart of an MRI machine. MRI stands for magnetic resonance imaging. It's a name that sounds complex, and the science behind it is indeed a Nobel Prize-winning symphony of physics, engineering, and quantum mechanics. But its purpose is beautifully simple: to create exquisitely detailed pictures of the inside of your body, and it excels where other imaging methods falter. While X-rays and CT scans are masters of visualizing dense structures like bone, MRI provides an unparalleled window into the body's soft tissues, the brain's delicate folds, the subtle texture of muscles, the intricate ligaments of a joint, and the vital organs that sustain us. It does all of this without using a single X-ray. That's a critical distinction. There is no ionizing radiation here. Unlike technologies that bombard the body with high-energy particles, MRI works by listening. It engages in a gentle, sophisticated conversation with the very atoms that make you, you. So, how does this incredible trick work? How can a magnet and radio waves reveal the hidden architecture of life? The secret lies in the most abundant substance in your body. Your body is approximately 60% water, and every single molecule of water, H2O, contains 2 hydrogen atoms. This makes hydrogen the most abundant element in your body, a vast, ubiquitous population of particles ready to serve as our microscopic reporters. Each hydrogen nucleus is elegantly simple. It's essentially a single proton. And because this proton has both an electric charge and a property called spin, it behaves like an infinitesimally small, spinning magnet. Think of it as a tiny compass needle, with its own north and south pole. Right now, inside you, trillions upon trillions of these atomic magnets are spinning away, pointing in every conceivable direction, a chaotic and random dance. But that chaos ends the moment you enter the MRI's powerful magnetic field. This immense, steady force, called the B0 field, acts like a powerful drill sergeant for those tiny proton magnets. The vast majority of them are compelled to snap into alignment with this field, all pointing in the same direction, like a perfectly disciplined army. They are now primed, organized, and ready for the next step. Then, the scanner introduces a second element, a quick, precisely tuned burst of energy in the form of a radio frequency, or RF, pulse. This isn't a random blast. It's a signal broadcast at the exact frequency that hydrogen protons are naturally inclined to absorb. This phenomenon is the resonance in magnetic resonance imaging. Think of it as a perfectly pitched musical note that only the hydrogen protons can hear. This pulse is a carefully calculated nudge. That resonant pulse gives the protons just enough energy to be knocked out of their comfortable alignment with the main magnetic field. They are tipped onto their sides, absorbing the energy in a quantum leap. Now, still spinning, they also begin to wobble around the axis of the main field, a motion called precession. All the protons are now precessing in sync, a coherent, spinning chorus. But this excited, synchronized state is temporary. The moment the RF pulse is turned off, the protons begin to relax. They release the extra energy they absorbed and realign with the powerful main magnetic field. As they relax, they emit their own faint radio signal, an echo of the pulse they just received. This is the crucial signal that the MRI machine is designed to detect. Highly sensitive antennas, called receiver coils, are placed around the part of the body being scanned. These coils are designed to be exquisite listeners, tuned to pick up the incredibly faint radio signals being broadcast by the relaxing protons. They are the ears of the machine. But how does a chorus of faint radio echoes become a crystal clear image of a human brain. This is where the true genius of MRI emerges. The raw signal is just noise. It contains no spatial information. We know a signal came from the body, but we don't know To solve this, the MRI uses a third set of magnets called gradient magnets. These magnets are switched on and off with incredible speed. This is what causes the loud banging and thumping sounds during a scan. They don't add much power, but they subtly and precisely vary the strength of the main magnetic field across the body. By making the field slightly stronger at one end and weaker at the other, they cause protons in different locations to pre-seess and emit signals at slightly different frequencies. This process, called spatial encoding, effectively stamps a unique address, a specific frequency and phase, onto the signal from every single point in the body. A powerful computer then performs a complex mathematical operation, a Fourier transform, to decode this symphony of frequencies. It translates the when and what frequency of each signal into a where on a 2D map. By repeating this process rapidly, it builds up a series of these maps, or slices, which can then be stacked together to create breathtakingly detailed 3D views of your internal anatomy. The final piece of the puzzle is contrast. Why does fat look different from muscle, or a tumor from healthy tissue? It's because protons in different molecular environments relax at different speeds. The rate at which they realign with the main field is called T1 relaxation. The rate at which they lose their synchronized wobble is called T2 relaxation. For example, fat molecules allow their protons to relax and realign very quickly. By timing the scan to be sensitive to this rapid T1 relaxation, fat appears bright on the image. Conversely, protons in water and other fluids lose their synchronized wobble very slowly. A scan sequence sensitive to this slow T2 decay will make fluid-filled areas, like the cerebrospinal fluid in the brain and spine, shine brightly. Muscle has its own characteristic relaxation times, giving it a distinct appearance that allows clinicians to assess its health and integrity. Even within the brain, the different water and fat content of gray matter and white matter creates a natural contrast, allowing for detailed neurological assessment. By skillfully manipulating these timings, radiologists can highlight specific tissues to diagnose a vast range of conditions. And the technology doesn't stop there. By adding special sequences, we can push the boundaries even further. We can create scans that are sensitive only to moving protons, allowing us to highlight blood flow in arteries and veins, a technique called magnetic resonance angiography. We can track the subtle directional movement of water molecules along nerve fibers, a technique called diffusion tensor imaging, which lets us map the brain's intricate wiring. We can even create cinematic loops, or cine-MRI, to watch joints in motion or see the heartbeat, chamber by chamber, in real time. So, what is the experience actually like for a patient? Understanding the science demystifies the process. Before the scan, you'll be asked to remove all metal objects and change into a gown. You'll lie down on a comfortable table that gently slides into the center of the scanner's tunnel, or bore. The key is to lie as still as possible, as movement can blur the images, much like taking a long exposure photograph. The one thing that surprises most people is the noise. The machine produces a series of loud bangs, thumps, and whirring sounds. This isn't a sign of malfunction, it's the sound of the gradient magnets switching on and off thousands of times per second to encode the image. To ensure your comfort, you'll always be given earplugs or headphones, often with music to listen to. A typical session can run anywhere from 15 minutes for a simple joint scan to over an hour for more complex neurological or body imaging. Throughout the scan, you can communicate with the technologist who is monitoring you from an adjacent room. While the procedure itself is painless and radiation-free, safety is paramount. And the number one rule of MRI safety revolves around its most powerful component. The main magnet is never turned off. It is always on, 24 hours a day, 7 days a week. This creates a powerful, invisible force field extending all around the scanner. Any ferromagnetic metal brought into this field can become a dangerous projectile. This is why metal is the biggest concern. This includes internal devices like older pacemakers, certain types of surgical clips or orthopedic implants, or even tiny forgotten metal fragments from old injuries, particularly near the eyes. Even a forgotten key in a pocket or a metal zipper can be pulled toward the magnet with incredible force, posing a serious risk. For this reason, every patient and staff member is screened with extreme care before entering the magnet room. You'll be asked a detailed series of questions to ensure you have no metal on or inside your body. In some cases, to get an even clearer picture, a special contrast dye may be used. This agent, which contains a rare earth metal called gadolinium, is injected into a vein. It circulates through your bloodstream and temporarily alters the relaxation times of nearby protons, causing blood vessels, tumors, or areas of inflammation to pop with bright contrast on the scan. It is generally very safe, but because it's cleared from the body by the kidneys, your kidney function will always be checked with a simple blood test beforehand. So the bottom line is this: MRI is a medical marvel. It is a testament to our ability to understand and harness the fundamental laws of the universe. It turns the tiny, spinning magnets inside every atom of your body into biological storytellers, broadcasting signals that we can translate into crisp, detailed, and life-saving images. It achieves this safely and non-invasively by listening to the body's subtle quantum song, not by zapping it with radiation. It's a reminder that within each of us lies a universe of complexity, and through the power of science, we have found a way to see it. That's a truly magnetic idea, isn't it?